Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 12, the graph of the equation y equals f of x. Classwork. Way back in Module 1, you graphed equations such as 4x plus y equals 10. By plotting the points on the Cartesian coordinate plane that corresponded to all of the ordered pairs of numbers x, y that were in the solution set. We called the geometric figure that resulted from plotting those points in the plane the graph of the equation in two variables. In this lesson, we extend this notion of the graph of an equation to the graph of y equals f of x for a function f. In doing so, we use computer thought code to describe the process of generating the ordered pairs in the graph of y equals f of x. Okay, so here's example 1. In the previous lesson, we studied a simple type of instruction that computers perform called for next loop. Another simple type of instruction is an if-then statement. Below is example code of a program that tests for and prints true when x plus 2 equals 4. Otherwise, it prints false. So it says, declare x to be an integer for all x from 1 to 4. If x plus 2 equals 4, then print true, else print false, and if next x. Okay, so let's interpret this output. It says the output of this program code is false, true, false, false. So what they're saying is, we're going to take all integers, for all integers from 1 to 4, if x plus 2 equals 4, then print true, else print false, and if next x. So what that's saying is, we take 1, substitute it in. 1 plus 2 equals 4. 1 plus 2 is 3. 3 does not equal 4, thus a false outcome. So it says, else print false, so it printed false, and if, then the next x. So then we put 2 in. So when we substitute in 2, 2 plus 2 equals 4, 4 equals 4, that is true, so therefore it printed true. It printed true. And then, and if next x, then it would plug in 3. 3 plus 2 is 5, 5 does not equal 4, therefore false. And then finally, let me circle that in red since it was false. False. And then finally we're going to substitute in 4. 4 plus 2 equals 4. 4 plus 2 is 6. 6 does not equal 4. Therefore, false. Okay, so notice that the if-then statement in the code above is really just testing whether each number in the loop is in the solution set. So it's plugging these values from the domain into this function and seeing if the solution set, which is 2, seeing if these numbers are in the solution set, for which 3 of them were not. Okay, page 2, example 2. Perform the instructions in the following program code as if you were a computer and your paper were the computer screen. Declare x to be an integer. Initialize g as the empty set. For all x from 0 to 4, if x squared minus 4x plus 5 equals 2, then append x to g, else do not append x to g. And if next x, print g. Okay, and the output was the set 1, 3. So an integer, so it's choosing integers from 0 to 4, right here. So if I plug in 0, I input 0. 0 squared is 0, minus 4 times 0 is 0. 0 minus 0 is 0. 0 plus 5 is 5. 5 does not equal 2. Therefore, it does not get printed out in our solution set. Then it chooses 1. 1 squared is 1. So let's just write these out because it's lengthy. So let me do this. 0 squared minus 4 times 0. 0 squared minus 4 times 0 plus 5 equals 2. Well, that's 0 minus 0 plus 5 equals 2. 5 equals 2. False. Then we substitute in 1. 1 squared minus 4 times 1 plus 5 equals 2. 1 minus 4 plus 5 equals 2. Negative 3 plus 5 is 2. 2 does equal 2. So that is true. Therefore, our value we substituted in, which was 1, is in our output set. Then we choose 2. So it's 2 squared minus 4 times 2 plus 5 equals 2. 4 minus 8 plus 5 equals 2. Well, 4 minus 8 is 4. Negative 4. Negative 4 plus 5 is 1. 1 does not equal 2. That is false. It is not printed. Moving on to 3. 3 squared minus 4 times 3 plus 5 equals 2. 9 minus 12 plus 5 equals 2. 9 minus 12 is negative 3 plus 5 equals 2. Negative 3 plus 5 is 2. That is true. So that is a solution. So 3 was our input, and therefore it outputs what value made it true, 3. And then finally 4. 4 squared minus 4 times 4 plus 5 equals 2. 16 minus 16 plus 5 equals 2. Well, that's 0 plus 5, which is 5. 5 does not equal 2. That's false. So we are done. We went from 0 to 4. We found 2 that made it true. So our output is the set that includes the numbers 1 and 3. Okay, discussion. Compare the for next if then code above to the following set builder notation we used to describe the solution set in Module 1. So this says the set of all x that are integers such that x is between 0 and 4 inclusive. Or I should say, x is greater than or equal to 0, or x is less than or equal to 4. And x squared minus 4x plus 5 equals 2. So what it's saying is we're taking the set of all x integers between 0 and 4 and just making a set of those that are between 0 and 4 and make this statement true. It says check to see that the set builder notation also generates the set 1, 3 whenever you see set builder notation to describe a set. A powerful way to interpret that notation is to think of the set as being generated by a program like the for next or if then code above. Okay, so where is the variable specified as an integer in both? So if we look at where they're specified as an integer, so if I look up here, it says for all x from 0 to 4 that our x's are integers, and here it says x integers between 0 and 4. So those match. So that's where they're alike. And then during each step of the loop, x is an actual number, 0, then 1, then 2, then 3, then 4, like we calculated here. Hence, it is possible to determine whether the equation x squared minus 4x plus 5 is actually true when it's equal to 2, or if it's false, which we did right here. Similarly, what does it mean for 0 less than or equal to x less than or equal to 4? Well, we could rewrite that. That's this right here. That could mean all x that are in the set of the domain. All x in D. Okay? And the x squared portion, minus 4x plus 5 equals 2, well, that is our function that we're checking, f of x. Okay? Okay, page 3, Exploratory Challenge 1. Next, we write code that generates a graph of a two-variable equation y equals x times the quantity x minus 2 times the quantity x plus 2 for x in the set -2, -1, 0, 1, and 2, and y in the set -3, 0, and 3. The solution set of this equation is generated by testing each ordered pairs x, y in the set. So we're going to take -2 and pair it with -3. That's right here. Take -2 and pair it with 0 right here. Take -2 and pair it with 3, and that's right here. And then they're going to take -1 and pair it with 3, -3 right here. -1, 0 is here. -1, 3 is here. And so on and so on and so on. And then they're taking 2 and -3, which is here. 2 and 0, which is here. And 2 and 3, which is here. They skipped 0 and 1, but did the same thing. So it'd be 0, -3, 0, 0, 0, 3, and then the same with 1. 1, -3, 1, 0, 1, 3. Okay, so they did this to see if it is a solution to the equation y equals x times x minus 2 times x plus 2. Then the graph is just the plot of solutions in the Cartesian plane. We can instruct a computer to find these points and plot them using the following program. So we're declaring x and y to be integers. Okay, if you look up here, let me get rid of all these little markers. Okay, so all of these and all of these are integers. So that's true. Initialize G as an empty set. So we're starting with an empty set. And then for all x in our set of domain, -2, -1, 0, 1, 2, and then for all y in the range, -3, 0, and 3. If y equals this equation, then append x, y to g, else do not append x, y to g, and if, next y, next x, print g, and plot g. Okay. So what it's doing is it's a computer program that's going to take -2 and pair it with -3, which gives us this point. That is then going to say if, and I'm just looking at this equation right here, if y equals, and our y is -3, equals x, which is -2, times -2, our x minus 2. Let me just move all this over. Okay, so we have -3 times y, or I'm sorry, -3 equals -2 times -2 minus 2. And now I just need -2 plus 2 at the end. Okay, so if this is true, then append the point x, y to g. Else do not append x, y to our set g in our empty set. Okay, so it's going to do the calculation. And I'm just going to simplify inside the parentheses first. -2 minus 2 is -4, and -2 plus 2 is 0. And as soon as I see this 0, I know there's a problem because this is multiplication, and anything multiplied by 0 is going to give us 0. That is not true. So this point, -2, -3, will not be appended to the set G. So when it comes down here, we'll get to that in a minute. But that's what we're doing. So test whether x, y is a solution. So that was not a solution. Loop through each y for x equals -2, then for x equals -1, and so on. See arrows in the table below. So that's what this is doing. I just did the first one. So A says, use the table below to record the decisions a computer would make when following the program instructions above. Fill in each cell with yes or no, depending on whether the ordered pair x, y would be appended or not. The step where x equals -2 has been done for you. So I just did -2, -3, and when we checked it, -3 did not equal 0, so that's this no right here. So then they went back and they plugged in 0 for y. So once you do this once, it's really easy. Then you just change the y. So now the y is leaving x -2, which we've already calculated, and putting y in as 0. And when I do this, well, guess what? That is not equal, but equal. So it's yes. And then they're going to ask you to try the same x and see if you get a positive 3 with that negative 2. Well, obviously it can't be 3 and 0, so that is a no. And we're going to continue this fashion. It may take a few minutes, but that's okay. So now I'm just going to use this area right here and just change the values. I only have to do the right side once for each of these numbers. Okay, so now let's just change colors to green, and now I'm going to do -1, and that is our x. So the x will be -1, that's this x right here, -1, and then -1 minus 2, and then -1 plus 2. I'm going to calculate this by doing the parentheses first. -1 minus 2 is -3, and -1 plus 2 is +1. And when I multiply these, negative times a negative is positive, positive times a positive is positive, 1 times 3 times 1 is a +3. So then we're going to check that with our 3 y's. So I'm going to put -3, 0, and 3 in. Well, it's obvious that -3 is false, so that's no. -3 is no. And then I go to 0, well, this is not a 0, so that's no. And y equals 3 is when it was true, so I'm going to put a yes there. Okay, so we really don't need to write that in every time, it's just too time consuming. Okay, so on to the next. I will change colors to blue, and now we're using 0. Plugging 0 in for x will give us 0 times 0 minus 2 times 0 plus 2. Well, I already know that this first 0, it doesn't matter what's in the parentheses, we're not going to get a value other than 0. Okay, so obviously -3 is going to be no. It does not equal -3, it equals 0. Our true was our 0, so 3 is not equal to 0, so this would also be no. Okay, so really once you get the hang of this, it's fairly quick. So now I'll change my colors. I'm now going to work the 1. Plugging it into here. So it's 1 times 1 minus 2 times 1 plus 2. Do the parentheses first. 1 minus 2 is -1. 1 plus 2 is 3. Positive times a negative is negative. Negative times a positive is negative. 1 times 3 is 3. So -3 will be my true. And -3 is obviously not 0. And -3 is obviously not +3. And then finally, one more time, we have to do the number 2x from our domain. Number 2 would be 2 times 2 minus 2. Okay, I already know what the outcome is going to be right there. And then 2 plus 2. No matter, we have a zero product property which says multiplying by 0, we're always going to get 0. So I don't care what these other parentheses are. I have a 0. 2 times 0 is 0. 0 times 4 is 0. My 0 is my true, so I put a yes here. And 3 is not 0, and -3 is not equal to 0. So there is our table for A. Okay, part B. What would be the output to the print G command? The first ordered pair is listed for you. So what they did was they took the yes. X was -2, y was 0, -2, comma 0. Okay, so where's my yes here? It's x is -1 and y is 3. Where's my yes here? It's when x is 0 and y was 0. Okay, and where is my yes in this one? When x is 1, y had to be -3. And then my yes in the x is 2. My yes was when y was 0. So it's the set of ordered pairs -2, 0, -1, 3, 0, 0, 1, -3, and 2, comma 0. Okay, this is page 4. I brought in the output from the prior page so we don't have to go back and forth. C says to plot the solution set G in the Cartesian plane. The first ordered pair in G has been plotted for you. Okay, so the 2, negative 2, 0 is right here, negative 2, 0. We're going to plot negative 1, 3 over 1 up 3, and it's right here. Plotting 0, 0 is the origin, is right here, and then 1, negative 3 is here, and then finally over 2 up 0 is right there. So there is plotting the solution set to the function that was given on the prior page. Exploratory challenge 2. The program code in exercise 3 is a way to imagine how set builder notation generates solution sets and figures in the plane. Given the function f of x equals x times x minus 2 times x minus 3, with domain and range all real numbers, a slight modification to the program code above can be used to generate the graph of the equation y equals f of x. And this is read the set of all ordered pairs x, y such that x is real and y equals the function f of x. Even though the code below cannot be run on a computer, students can run the following thought code in their minds. So what they're saying is the computer would be generating forever and ever because there are infinite values between two integers. And a lot of people have difficulty thinking about that, but I could have the point, the number of values between 0 and 1 is infinity. I could have 0.01, I could have 0.001, 0.0001, 0.00001. I can go on forever and ever and ever out infinitely number of digits, and it's not equal to 0. So therefore there are infinite values between each integer, and that's why a computer cannot run this. So even though the code that cannot be run by our computer, students can run the following code through their minds, means that we can kind of understand what is going on in between, and we would connect the dots with an arc or a curve or a straight line. So test whether xy is a solution. For each x value code, loop through all y values where x and y are real numbers. So it's the same thing except we changed an integer to real. Okay, page 5. A. Plot G on the Cartesian plane. The figure drawn is called the graph of y equals f of x. So I'll use green this time. We're going to plot the points that were in our output for the integers. Negative 2, 0 was here. Negative 1, 3 is here. 0, 0 is here. 1, negative 3 is down here. And then over 2 up 0 is right here. So this graph matches our graph from the last question. This is integers, but we are asked to graph not just integers, but all real numbers, so every value in between. So just to get an idea as to what this is doing, it's hard to picture it right now. It just looks like a bunch of dots all over the place. We can pick a value that's not in our set and check it. Okay, so here is our function. F of x equals x times x minus 2 times x plus 2. So if I choose a value, let's go out to negative 3. So I want to know what f of negative 3 is. Again, this is an integer, but what'll get us started? Here's negative 3 minus 2, and negative 3 plus 2. So that would tell us that f of negative 3 is equal to negative 3, do the parentheses first, negative 3 minus 2 is negative 5, and negative 3 plus 2 is negative 1. So f of negative 3 is negative times negative, which is positive, times a negative is negative, 3 times 5 times 1 is negative 15. So this is way down here. So what that means is if I were to connect those two dots, this function is going way down here somewhere. And it's not going to get to negative 3 until we're at negative 15, which is way down off this page because this only goes to negative 4. Now, if I pick a point between negative 1 and negative 2, I'm trying to figure out how I got up here. Well, if I plug in or substitute in negative 1.5, that's f of negative 1.5. So let's just do that. just to give you an idea of what's going on in this graph. So if I put a negative 1.5, negative 1.5, f of negative 1.5 equals negative 1.5 times negative 1.5 minus 2. I'm just going to skip a step here, so I only need 2 of these. Negative 1.5 minus 2 is negative 3.5. Negative 1.5 plus 2 is a positive 0.5, or 1/2. So when I do that, I'll use my calculator for this. Okay, so if I get the calculator, negative 1.5 times negative 3.5 times a positive 1/2, or 0.5, is 2.625. Negative times a negative is positive, positive times a positive is positive, and we got 2.625. So that's a negative 1.5 and up to 0.625, which is about here. So what's happening is this is coming up like so, and then it's turning, and I'm not going to take time to add any more values, but it's turning and coming back down. So it's choosing every value in between each integer. And to get from here to here, we'd have to draw a line down sort of like this, and it's going to curve and turn and come back up to 2, and then continue over like so. So there is a rough sketch. I apologize for the lack of neatness, but it's hard to draw with this pad. So this is the function f of x graphed with every point in between. Let's just get that out there. Okay. B says, describe how the thought code is similar to the set builder notation, the set of all x, y, such that x is real and y equals f of x. Okay, so the answer is both generate sets by checking every point x comma y in the Cartesian plane, searching for points x comma y for which the equation y equals x times x minus 2 times x plus 2 is true. So in other words, what they're saying is the function f of x is all the values on this curve, if you will, including the solutions that were integers from the first set. So it checked that those were in both. Part C says a relative maximum for the function of f occurs at the x coordinate of negative 2/3 square root 3, comma 16/9 square root 3. Substitute this point into the equation y equals x times x squared minus 4 to check that it is a solution to y equals f of x, and then plot the point on the graph. Now you might be wondering, where did they get this function from? Okay, and they have this. Well, what did we have? We had x times x minus 2 times x plus 2. Well, x minus 2x plus 2 is x squared minus 4. So x minus 2 times x plus 2, with this x in front that we have here in our original f of x, or y equals, well, all they're doing is FOIL, or the distributive property, x times x is x squared, x times 2 is 2x, negative 2 times x is negative 2x, and negative 2 times a positive 2 is negative 4. These two terms are opposites, they cancel out, and we're left with x squared minus 4. So that's where this came from, for starters. Okay, hopefully that makes sense to you. And they're telling us that a relative maximum, well, that means it's a relative maximum is a maximum relative to a certain range, or domain, I mean. So if I chose this value to this value here, a relative maximum would be the maximum value right here in between in that domain. So this is a relative maximum, but notice that this function continues up here. So this point up here is higher than this point over here, but relative to this domain, this is a maximum in here, even though it goes higher somewhere else, if that makes sense to you. That's what a relative maximum is. Okay, so it says a relative maximum for this function occurs at the coordinate here. Substitute the point in and check to see if it's a solution. So this is x. This is our x. So y, well, no sense in writing y because this is our y. So I'm going to write y equals 16 over 9 square root 3. That is our y, equals our x, which is negative 2/3 square root 3. That's this x times negative 2/3 square root 3 squared. That's this x squared minus 4. So all I did was took this and plugged it in for y, and took this and plugged it in for x here and here. And that's how I got this. So now we're going to simplify. This is going to stay 16 over 9 square root 3 equals, and let's first work on this portion here. So I'm just going to bring this down. Negative 2/3 square root 3 is going to stay there for now. I'm going to square this. When you square something in a parentheses and there's a number and a radical, you have to distribute the squares. So a negative times a negative is positive. 2 squared is 4. 3 squared is 9. And the square root of 3 squared is simply 3. So I'll make that 3 over 1 minus 4. Okay, just made some more room for us. Now this is going to stay. Okay, I clicked there, thank you. This is going to stay 16 over 9 square root 3 equals. And I'm going to, let's see, I need another parentheses here. That's still a parentheses times negative minus 4. So I'm just going to bring down negative 2/3 square root 3. And that's times, and 4/9 times 3 is 12/9. 12 over 9, which reduces to 4/3. So this is 4 over 3 minus 4, and 4 over 1, and I want a denominator of 3. We multiply the top and bottom by 3. That's 12/3 or 4. So minus 12/3. Okay, so this is going to simplify to 16 over 9 square root 3 equals negative 2 over 3 square root 3 times 4 minus 12 is negative 8/3. So when I multiply this, I get negative 2 times a negative 8 is positive 16. 3 times 3 is 9. And then I have my square root 3. And as you can see, it's true. 16/9 square root 3 equals 16/9 square root 3. Okay, so check to see that that is a solution, and then plot the point on your graph. Well, 16/9 square root 3, what is that? Well, 16/9 for starters, let's do that first. 16 over 9 is 9/9 plus 7/9, which is 1 7/9, almost 2. And what is the square root of 3 as an approximation? .73205 ... Okay, it goes on and on and on. So 1 7/9 times 1.73. If I just put the whole thing in my calculator, 16 divided by 9. Forgot my parentheses. I always want to put fractions in parentheses. 16/9 square root 3 is 3.07, a little bit more than 3. And that is our y. So y is 3.07. That's approximately 3.07. So this 16/9 root 3 is approximately 3.08. And that is our y. So we have the point 3.08, and our x is negative 2/3 square root 3. So negative 2/3 square root 3 is approximately negative 1.15. Did that round down? Yeah, negative 1.15. Okay, so what that means is I want to go to negative 1.15, 3.08. Okay, so I moved the point up here so we can see it. Negative 1.15 is around here somewhere, and 3.08 is just above 3 here, so it's right here. So in all actuality, my graph is not correct. This should have come up like this, higher, and then down, like so. All right, so knowing a relative maximum helps us determine how to plot these points. So it actually came up to this highest point here, back down to the point negative 1, 3, which is in our set, and then continued down. So we can't assume this is a minimum either. It's probably going a little bit lower over here. Okay, and so that's how we plotted the relative maximum on our graph. Okay, page 6. Part D says a relative minimum. Okay, so now we're talking about a relative minimum for the function f occurs at the x-coordinate 2/3 root 3, negative 16/9 root 3. A similar calculation as you did above shows that this point is also a solution to y equals f of x. Plot this point on your graph. So I've already brought this over to here, so there it is right there. And keep in mind that this one that we already calculated as an approximate decimal, so we know where it is on the graph, was negative 2/3 root 3 was here. So 2/3 root 3 would be the positive of 1.15. So it would be the point 1.15, comma, and 16/9 root 3 is now negative 16/9 root 3. So this 3.08 will be the opposite, or negative 3.08, without having to use our calculator again. 1.15 is approximately here, down 3.08, which would probably be about here, or 3.1 almost. So again, our graph did not turn here. It continued down to this point and then turned up, like so. So the purple here would be more accurate than the green was. We didn't get to our minimum. Our relative minimum was right here. Okay. E, look at your graph. On what interval is the function f decreasing? So if we go back to the graph, I'll do the decreasing portion of the function in red. So it's decreasing from our relative maximum here down to our relative minimum here. So it is decreasing right here. It is decreasing from x equals this, and it's decreasing until it gets to x equals this. So it's decreasing from this x value all the way over to this x value. So if we're looking and we're going this way on the x-axis, the function is moving down as we move to the right on the x-axis. So it's decreasing from negative 2/3 root 3 to 2/3 root 3. Okay, and since that's a maximum point, we don't use a bracket like this because it's not decreasing at that maximum point. That's where it turned. It's not increasing nor decreasing there. It's kind of stopping and turning and going the other direction. So we use parentheses, not brackets, just to be clear on that. And F says, look at your graph and what intervals, plural, is the function increasing? Well, let's use black for this one because I haven't used black yet. So the function is increasing right here. I'm going up as I draw it, am I not? And it's increasing until I get to this point right here, and then it turns and decreases, and then it turns at this point, and then it starts to increase again. So there are two intervals. And this is decreasing forever and ever and ever, which goes to negative infinity. And this is increasing forever and ever and ever, which is going to positive infinity on the x-axis. As we go to the right forever and ever, this is still going up. As we go to the left forever and ever, this is still going to go down. We just need to indicate our points where it stops increasing, which is the point negative 2/3 square root 3. So my interval is from negative infinity to negative 2/3 square root 3. So it's increasing from negative infinity until it gets to our relative maximum. And then it's increasing again from our relative minimum until positive infinity, or forever. So those are the intervals in which that function was increasing. Okay, page 7 is the end of lesson 12. Review the lesson summary and go do your problem set.